So yes, as promised, this is a talk on how stellar migration can impact the enrichment history of the Milky Way. And before I get going, a big thank you to the organizers and everyone involved. I've really enjoyed hearing about everyone's awesome science. So without further ado, let's get going. So there's in-depth discussion of a lot of observables in the paper, but for the sake of this talk, I'm just going to focus on the age abundance relations. So starting on the right over here, this is the oxygen abundance against age taken from Diane Foyet's 2018 paper. And the takeaway is that it has this interesting sort of C-shaped profile where the youngest stars are the solar metallicity stars, and stars of super and subsolar metallicity have systematically older ages. So this was a surprise. In general, we expect classically enrichment to proceed alongside star formation and thus time, and that would predict a more or less monotonic age metallicity relation. Pivoting to the left, this is the alpha to iron ratio against age. And there's this interesting population of outliers, young stars that have too high of an alpha abundance for their age. And there's been some discussion about whether these are the impact of stellar interactions making stars look younger than they actually are. But there's also been some arguments that say that some of these are truly young alpha enhanced stars. So then the question becomes, how do they get those abundances for that age? So we want to study these populations in the context of radial migration. So if you want to do radial migration in chemical evolution models, one of the one way to do that is with hydrodynamical simulations. That's perhaps one of the most self-consistent ways to take a given star formation history and dynamical history in one realized galaxy. But if you want to play around with assumptions of the time scales on which stars are moving, maybe the star formation history, then hydrodynamical simulations just aren't the ideal laboratories to do that with. So what we do here is we instead take an approach where we put these concentric rings down to describe the disk of the galaxy. And each ring is described by a one-zone model with, a gas mass, a star formation rate, and so on. So multiple one-zone models stitched together, hence the name multi-zone model. And so stars are migrating then by just simply taking information from a hydrodynamical simulation like so. So we take this H277 simulation from the N-body shop folks at the University of Washington, and we take a very simple approach of just, for a stellar population that forms at a radius r and time t, find a star particle from the hydrosim that formed at a similar radius and time, and tag it as an analog. So the stellar population then takes its analog's change in radius, not its final radius, its change in radius, and its present day midplane distance just at face value. So then it migrates from its formation radius to its implied final radius with a square root of age dependence. We did play around with this assumption in the paper, so if you're interested in what happens when you play around with that, check out the paper. But one of the most important things for understanding what's going to come up later is that these stellar populations are ejecting nucleosynthetic products as they migrate. So for delayed enrichment sources like type 1a supernovae, they're not producing iron necessarily at the birth radius. If a star doesn't move far, it might be the birth radius, but overall, they're going to be injecting iron on a distribution of radii, as opposed to just one radius. So we take these models and we feed them to the versatile integrator for chemical evolution, or VICE for short. So for the sake of this talk, this is just the software that we feed this model to. But I want to take a minute and just advertise it real quickly, because I think this is a powerful tool that folks in this audience would find nice and useful. What we're really going for with this code is a one-size-fits-all chemical evolution library. And what I mean by that is that a lot of the parameters that you would put into a chemical evolution model, like nucleosynthetic yields, your star formation history, your IMF, even your mixing processes, are all just user-defined mathematical forms. You can do really whatever you want with them. So to put a little detail to that, everything I just went over on the previous slide, this is all input to VICE. You can change all of this without even modifying the source code. So if you have a chemical evolution model, and even if it looks nothing like mine, odds are Vice can still handle it. And as a bonus, it's really fast. It's got a backend written in C, so it gets that nice turbo boost on its speed from a compiled library. Well, after that word from our sponsors, back to the science at hand. So this here on the right, just before I get into what's going on, I'll talk about what's plotted. This is the oxygen to iron ratio. We're taking oxygen as the representative case of an alpha element here, and plotted against age for all of the stars that are in this the solar neighborhood at the end of the simulation. Black squares are just some measure of the population average trend, and red triangles are Diane Foyer's measurements from 2019. So, all else aside, what I just want to emphasize is that we get this population of outliers, these young alpha-rich stars in the solar neighborhood. But how do they arise? So for that, pivot over here to the left. This is showing the oxygen to iron ratio against the metallicity in the gas phase. These are the evolutionary tracks, so early times up here, late times down here. And flanking it is the type 1a supernova rate. So, overall things are relatively smooth, but this is without radial migration. So this is if stars are just staying where they're born, they're not moving at all. This is the type 1a supernova rate and gas phase evolution that you get with time. But when we let stars start moving, these dotted lines become these solid lines. So what's happening is as stars are moving, radial migration can give you some excess or deficit of enrichment as a function of time. And so if that excess or deficit is sustained, you can achieve an iron-rich or iron-poor ISM. And then the stars, obviously, when they form out of that ISM, they inherit that chemical composition and can migrate to the solar neighborhood. Where then, if they show up in observations, they show up as a young and alpha-rich star, but they're not so much alpha-rich as they are iron-poor. And it's because they were born out of an ISM that just didn't sustain as many type 1a supernovae for some time. The star formation history has an interesting impact on both the alpha to iron ratio and age metallicity relation. So down here in the lower left, we're just comparing an apple and an orange. They're not necessarily a best fit apple and a best fit orange. They're just two models that are simple that we can run with. So the dotted line is a star formation history that does not have a starburst at recent times, and the solid line is one that does. It's about a factor of 2 in the global star formation rate. In the top right up here, this here is the same panel as the previous slide. So that's the no starburst case. But over here on the right, this is the case where there is a starburst. So somewhat unsurprisingly, you build in a starburst into the model, you make a whole bunch of core collapse supernovae. Those produce a lot of alpha elements, but not so much iron. So then you get this late alpha enhancement for young stars, which just simply isn't seen in the data.
2 minutes.
Thank you, Keith. If we turn to the age metallicity relation for here parameterized via O on H, this is the no starburst case in the top row, and the starburst case in the bottom row. And each panel is just a different bin and radius. So inside, somewhat inner disk over here and outer disk over here. So if we focus on the solar neighborhood, here the black squares are still some population average trend against Diane Foyer's measurements in red. For the most part, either model really does fine in the solar neighborhood. Since these aren't best fit cases, we can't really rule out one or the other looking at just the solar neighborhood. But if we look at other other bins and radius, we find that actually there are some subtle improvements that the starburst model makes on the no starburst case, which is in the inner galaxy, we tend to be systematically over predicting ages. And by making a bunch of young stars outrightly, we mitigate that problem for some metallicities here between 5 and 7 kpc. In the outer galaxy, especially, the starburst case does a lot better at reproducing the shape of the trend. You can kind of make the same case that for a lot of metallicities here, the characteristic ages are over predicted, and that problem is also mitigated by the starburst case. So we're getting kind of conflicting stories between these models where the age-metallicity relation seems to favor a starburst scenario, whereas the age alpha to iron relation seems to reject that. So in conclusion, the young alpha-rich stars in the solar neighborhood can be understood by considering a variability in the type 1a supernova rate with time, and the stars that might form out of an iron-poor ISM that then migrate to the solar neighborhood. This recent starburst is telling us some conflicting things about which model for the star formation history to favor. Different observables are favoring different models. There's more discussion of this in the paper. So if models for the Milky Way with migration and observables like the age-metallicity relation, distribution functions, we also go into the infamous bimodality in alpha to iron. If that's science that you like, then I encourage you to check out the paper. And lastly, Vice is publicly available. I hope a lot of you check it out and find it useful. I hope it enhances your workflow. And if you do, don't hesitate to ask for help. I'm here to help you get going on that. So with that, thank you. I'll take questions.
Great, thank you very much. Are there any questions? I'll also clap as well.
Thank you.
And do a clap. And Furkan asks, firstly, thank you for this good presentation. Did you share the model codes on your GitHub? I want to learn Vice. If I will have a question, can I ask you another time?
Absolutely, yes. So there's so Vice. If you go to the PyPI page there's a pip installer. There's links there to the source code documentation. There's also the bug tracker, and in the source code on GitHub, there's everything that runs our models from this paper that was submitted back in March. The source code that runs those models and makes all the figures can be found there, as well as the source code for models and figures from the 2020 paper, which originally put out Vice. There's also a tutorial in the repository. So if you run the pip installer, and there is a functionality that launches the tutorial and documentation from the command line as well. So.
Great. Melissa has a hand raise.
Thanks. Yeah. Thanks for the talk, James. Sorry, I'm losing my voice. It's really interesting. I have a question. Reading your paper, I remember, and forgive me if I'm misquoting. You say you couldn't fit the entire oxygen plane, and more dramatic evolutionary pathways are required. Can you expand a little bit on?
So in the so that is that's speaking more about the oxygen to iron distributions. We found that in our models, we formed too many intermediate alpha stars to reproduce the bimodality in alpha to iron. So when we say more dramatic pathways, we mean one way to do that. There's some debate about this, and Sanjeev Sharma's excellent talk from a couple of days ago is an excellent counter argument to this. But we find that when we put in our inside out galaxy growth with radial migration, it's hard to not populate that region of intermediate alpha space. And so a way for us to mitigate that would be to shut off star formation for some time, or more complex star formation histories. There's a bunch. There's more theories for how the bimodality might arise. That's just one of them. But yeah, so there's some future work where we're going to be complicating the models in interesting ways to see if we can get it.
Great. I think unfortunately we only have time for one more question, so I'll read Paula's question. How did you test star formation burst produced after the merger with Gaia Enceladus, example 7 to 8 gig years ago?
7 to 8 gig years ago. Excellent question. When we were first putting the paper together, Sarah Loebman, who's on the paper, I think also asked about that, and that's a star formation history we haven't considered yet, but it is on the to-do list, so stay posted. Excellent question, Paula. Thank you.